So these are three different ways of looking at essentially the same problem. So if I can begin saying that I want to look at a molecule and see how it goes. Can you say what are the two things I need to take care of if I want to look at a molecule and see how it goes? We obviously need its position. Where is it? Another thing which we need is very good. It's momentum, but since mass is constant, we are only considering velocity. So we already know the position. And why do we need the velocity? We need the velocity to see where will the next position be. And how do we get this velocity? We have a molecule. It has a certain velocity. Now who gave that velocity? How on earth did it get that velocity? Obviously because there is something else which is causing it to move. If it is stationary, it has to be stationary. Newton's first law of motion. And if something is stationary, it has to be stationary. It has to have an external force acting on it so that it has this velocity. So this velocity is got by a certain potential around its current environment which is causing it to move. It is not moving because it is gaining some sort of change all of a sudden. It has a potential around it. And this velocity is related to that potential as well. So if we know x0 at time t0, then obviously say that I know x1 at a certain time t1. Right? And this velocity, as I was saying, is got like this. It's fine. So this force, as you can see, is a negative gradient of potential. So it has a certain potential around it which is causing it to have a force, and from that force it is having a certain velocity. Now we are still here talking about the whole thing in an inertial frame of reference. So we are observers from outside and we are just observing what is happening inside. So what does this thing essentially mean? Very simply stating, but the velocity will be a constant if the force is zero. So this part is clear. Now, going back to our previous problem of looking at the molecule. Yeah, that is great. It's nothing but one dimension. It is 4 dimension, y, z, everything. Okay? So, if we have a certain molecule over here, we need to know about its position, which is x1, y1, z1. And now, using Newtonian mechanics or Hamiltonian mechanics or Lagrangian mechanics, we want to predict where does it end up. And why do we need it? If we can show this, we essentially know reaction mechanisms. This is how mechanisms are happening. You can explain electron transfer. This is how electrons are transferred. And lastly, spectra. We can also look at spectra of molecular physics. But the problem is, maximum reactions which happen, they do not tend to follow this whole thing. They follow something else. But there are major reactions which follow just like, and we can get interesting properties without actually doing the experiment and just with a pen and paper. Fine. So now, let us look at something else. So now I'm going to define a certain quantity. Define a certain quantity. There is no logic as to how it came into being, why it came into being, but I'm just going to define it. This quantity is known as action. This thing is defined as action. And what is this L over here? This L is known as the Lagrangian. Now, what is the Lagrangian? It's a kinetic energy minus the potential energy. We will see something like this popping up once again in Hamiltonian mechanics, where it will be kinetic energy plus potential energy. So, as of now, I am relegating myself to the Lagrangian, where it is the kinetic energy minus the potential energy. And if we take an integration over time from 0 to a time t, we get something known as action. Now, let's look at it differently. Suppose I have a molecule over here, or rather, a ball, a certain ball, at position B. It goes after some time to a position B. Where essentially many paths this ball can take from going from A to B. And for each of these paths, we can define this action as S1, S2, S3, so on and so forth. So each of these paths will have a certain action. Now, classically, when I am saying classically, I mean the thing which we can observe, something which we can observe, will be the path for which this action is at the extreme. So the change in action for a particular path, if it is 0, we will say this is the path which the particle has formed. For the other paths, they may not have the del S equal to 0 immediately. They have a certain probability of going from this point to the next. But what is happening classically, or rather what we can see, what we can observe, is the very path which has a delta S of 0. There will be only one. There is only one path whose delta S will be 0. And no, so there are some constraints to this whole thing. The first constraint being, since it is going from a position A to a position B using different paths, the positions of these 2 points are not changing. The endpoints are fixed. This is important. The endpoints are fixed. So, let me write over here. The endpoints are fixed. So whatever things which we are trying to do in these paths, they cannot happen to A and B. You can think of them as 2 points of a string, and I am holding those 2 points together. Now I can tweak this string. The string can take a lot of forms, but the endpoints are still fixed. This is important. So when I say that del S will be 0, and I define S as this, I can write del S something like this fine. So since the Lagrangian over here depends on x and x dot, so you know what is x dot? It's velocity. So where does this velocity is coming from? It's coming from the kinetic energy. It's half mv square. So it's essentially this kinetic energy is dependent on x dot. And this potential energy is dependent on x. That's the position. So when I am doing a delta s, I need to keep the change between delta x and delta x naught. Sorry, delta x dot. Fine, the mathematics has been fine so far. Okay. So this delta x dot is something like this. It's fine. So now I'm doing the integration of the first quantity. So this term I have just kept it like this, and now I'm going to do a differential integration by parts for this second term. Okay. So this will give me fine. So, integrating this term by part. So, first the integration over this quantity giving this same, and if I integrate over this, integration over this ddt will vanish, and I will just be left with del x, and this del x is over here. Next thing, I will do a differentiation of this part, which I have done. And this del x will again come over here because it's another again an integration over the whole thing once again. Now comes the important part. The important part is this quantity delta x from 0 to t. Okay, the change in x, this x from 0 to t will be 0 because my endpoints are fixed.
Zero time it will be at one locus, 1 point A, t time. Should be at B, or if you take it as going from A to B and back and it's coming back to B. Is that the case?
So, look at it once again. Looking at the change of del x over here, looking at a delta x. So, since my endpoints are fixed, this delta x essentially will be 0. Now what we are left with it's fine. And as I said, for the classical path, the delta x should be 0. I'm looking at it for a classical path. I put this quantity to be 0. So if I put this quantity to be 0, this quantity should also go to 0. And we end up with something like this. This form. Gaussian equation. Fine. So what if I have to essentially done? We have defined a quantity known as action and looked at the dynamics of a particle going from a certain point to another point. We have minimized the action or maximized it. We have located the extremum of S. I am not saying we have maximized it or minimized it. We have located the extremum of S and we landed with an equation which looks like this. And L over here is the Lagrangian. So now one may say that you suddenly define the quantity known as action and you end up with this equation. How can I say that whatever you are saying is correct? I have been defining quantities all the while. I defined this and then I defined maximum should be 0 and then I got a thing like that. One can obviously question that how are you saying that the definitions we should have given is correct? So then I say that okay, Newton's laws are correct. Newton's laws are correct, right? I may be wrong. I may be defining everything wrong, but Newton's laws are correct. So what I do is, you see, I take the Lagrangian derivative. So what will I be getting? L is what? Kinetic energy minus potential energy. I do del L del x. The kinetic energy doesn't depend on x, it depends on x dot. So it goes to 0. Why it goes to 0? Because I am taking the partial derivative. So what we remain with is minus of potential. So minus del V del x, right? Now, what is the other quantity? ddt of del L del x dot. Take a differential with respect to x dot right of the kinetic energy. Okay? So if I do the differentiation, keeping matters simple, but if you want to make it complicated, I don't have any issues. Right? The Euler-Lagrangian form says that these two should be equal. Looks familiar? This is known as Newton's second law of motion. That the gradient over potential with respect to position is a derivative of any force. So essentially what we have defined led us to the correct Newtonian equations, and we will say with certainty that these definitions are correct. Fine? So I'm drawing this out. So now I have a bunch of equations. First equation is so this is second order equation. These are two first order equations. So when is the equation in second order? When we are in the coordinate space of x. But I have defined x to be my coordinate system. If I want to look at a certain Cartesian graph of x versus t, then I can perfectly plot this mx with the help of this if I know the potential field. But there I will need to solve another differential equation which can be transformed. However, if I define a new space with respect to x and p, this is p dot, just x and p, then I will have two first order equations which make life simple. Oh, sorry. So if I define it with respect to p and x, I end up with two first order equations which make life easy, and more than that, easier to visualize. So that is why I want to bring in a new concept of a new space between p and x, and I will name this as phase space. Fine. Now, why is this phase space useful? This phase space is essentially useful because it helps us visualize certain things in chemistry. For example, the typical example being a simple harmonic oscillator in a very easy way. Have you ever tried plotting a simple harmonic oscillator in the Cartesian coordinate? It's very tough, it's difficult. But if you do it in the phase space, life becomes very easy. Just giving you a small taste of why life becomes easy. So what are we plotting? We are plotting the energy of a simple harmonic oscillator. So what will it be? V square by 2L plus certain Vx. This V is dependent on x. Isn't this such a Vx को भी I'm writing as half kx square. And this is for a simple harmonic oscillator, right? Isn't this the equation of an ellipse in the phase space, obviously? So we can just visualize the energy as different ellipses. So suppose this is another ellipse, this is another ellipse, and these will have E1, E2, E3 energy. See, life becomes simple if you want to the phase space. Anyways, let's not talk about phase space right now. I don't want to go into complications. Now, moving on. So when we go to the phase space, remember, we are for n nuclei. How many coordinates are we dealing with right now? We are dealing with essentially 6 n coordinates. Why 6 n coordinates? Because P will give me Px, Py, and Pz. X essentially is x, y, and z. So for each dot, we have 6 coordinates. For n nuclei, we have 6 n coordinates. So it is a 6 n dimensional vector space. And the vectors going to coordinate. Okay. And lastly, a very brief introduction to Hamiltonian mechanics, like H, kinetic energy plus potential energy. So in the phase space, I want to differentiate with respect to x to see how is the Hamiltonian changes with respect to x coordinate. Another time I differentiate with respect to p to see how the Hamiltonian is changing with respect to p. What is my Hamiltonian? It's essentially a measure of my energy. So these two equations will tell me how is the energy changing in the phase space. And since these are just first order equations, life becomes simple. visualization becomes. So this is what I wanted to say about Hamiltonian equations, Newtonian mechanics, and Lagrangian equations. So can you understand that if we know these two equations, we know everything about that particle which we are looking at. We know everything. We know its, if we know its, we know how it will go to a certain point if we know the potential around it. And how do we know the potential around it? If we have a certain, let's begin some chemistry. So if I have a reaction going on, I have a solvent, I put some molecules in the solvent. So molecule will have a certain solvent cage around it. That cage will lead to a certain potential. That potential is this V. I know the values of the potentials, I can experimentally find out the values of the potentials, or I can theoretically give it some potential I want. From there, I will be able to know how is that particle moving in the phase space, and if I want to look at the Cartesian coordinate, I will do a transformation from the phase space to the Cartesian space. So it becomes simple, I know everything what is happening. So far so good. So this was all I wanted to say regarding classical physics.